All right, welcome to thermochemistry. We're going to talk about a couple of different things in this video, and so it's just going to kind of get us introduced to it. But being thermo, one of the things that we're going to talk about is energy. And energy, as you might know from physics, maybe, is the ability to do work. That's probably the physics part that you've learned. The part we're going to make sure that we also add on, because it's true, is an and or transfer heat. So this is important in terms of just a few kind of equations that we need to know. First of all, work, which we're going to designate W. You guys know is force times distance. You guys know that from physics. You know, if you push on a wall and it goes no distance, you did no work, right? So another thing that we are going to add on, and something you learned in Chem 1, is heat flow, Q. And heat flow is a movement of energy that causes a temperature change. Remember, delta means change. So when we talk about energy and its relation to heat and work, one of the important equations that we're going to be looking at is this one. Delta E is equal to Q plus W. And then we need to know a few things about Q and W, not numerically, but with the signs for that. So let's just take a moment to understand sign conventions in chemistry. When we talk about sign conventions, when I talk about signs, I mean plus and minus. Sign conventions are told from the system's point of view. So we'll see this here in a second. So one of the signs that you learned about in Chem 1 is that Q could be positive or Q could be negative. And if you think about it from the system's point of view, if Q is positive, it's literally the system is gaining heat. The system is gaining heat, pulling heat from the surroundings around it. It is endothermic. So the surroundings around it get cold. The system itself might get warmer, or it might use that temperature or that energy to break bonds or cause something else to happen. If Q is negative, then the system is losing heat, and so that's exothermic. And so those should be familiar to you. Well, the same conventions are going to apply with work. So work could be positive or work could be negative. And again, it's based on the system's point of view. So if work is positive, that means that the surroundings are doing work on the system. It's almost like the system's gaining work. That doesn't really make sense in that way, but that's sort of the idea. If work is negative, then the system's going to be losing work, so to speak. How is it going to do that? Then that means that the system is doing work on the surroundings. Great. So those are some of our sign conventions. So let's just think about a scenario here. Let's envision I have a cylinder, and in that cylinder there's some kind of reaction taking place, and that cylinder has a movable piston, so like a little lid that has the ability to move up or down depending on what happens in the reaction. So let's say that this reaction gives off a gas, so pressure builds up, and let's say that that piston ends up moving up to a new location up here. Well, the volume increased, right? The volume of the gas. So I want you to think, pause the video if you need to, if the volume increases, is work positive or negative? Is the system doing work on the surroundings, or is the surroundings doing work on the system? Well, the system pushed, right? The system pushed that piston up. And by pushing that system up, that meant the system is actually doing work on the surroundings, which is the piston. So in this case, work is negative. If on the flip side, that piston had moved down, maybe it used up a gas, right? And it actually dropped, then the volume would have dropped. Well, what would have dropped the piston? Well, it would have, because air pressure would have pushed it down. And that would have been a case where the surroundings were doing work on the system. And so work would be positive. So just a different situation. So we're using work, and that's something you use in physics all the time, but you know, we're not talking about pushing a desk or a car or something like that. We need to talk about chemistry work. And so let's take this physics definition, work is equal to force times distance, and let's make it a chemistry definition. So if you move something, you know, work is equal to force times, we're going to call it a change in distance, like it started at distance 0 and it ended up at distance 2 meters, for example. All right, we're going to do a little algebra. So that means that work is equal to force times the change in distance cubed over distance squared. Just think about it algebraically, right? Distance cubed over distance squared is the same as distance. I'm going to manipulate that. I'm going to make it force over distance squared. I'm just going to move that times distance cubed. All right, this is force over distance squared. That's force over area. In your mind, you're just saying, I know what force over area is, right? That's pressure. The change in the distance cube is the same as what? Volume. So what that means is work is equal to pressure times volume. Oops, let's times change in volume because we had a change in distance. So if our volume was 1 liter and now it goes to 3 liters, our change in volume is 2 liters. And then we're going to go ahead and add a negative to that. And that negative is solely there to make sure it fits the sign convention. So that if the system's doing work on the surroundings, so it ends up with a negative value for work, or if the surroundings are doing work on the system, it's a positive value. So that's the idea. All right, that's going to be playing a role to us down the road, but this is another equation to kind of have in your head. One of the things that we do in thermochemistry is to really think about measuring changes in energy, changes in heat, all of those things. And so we will measure our changes in energy and our changes in heat via a calorimeter. And there's 2 types of calorimeters we're going to look at. One we're going to spend little time on, and that's this one, the bomb calorimeter, which sounds really cool, like it's going to explode, and it doesn't explode. And then another one, the coffee cup calorimeter, which sounds super exciting. No, it doesn't, right? It's a styrofoam cup. That's all this one is. But at least I want to address the 2 ideas. They're used for different things. Bomb calorimeters are used when you're at a constant volume. Coffee cup calorimeters are used when you're at constant pressure. I'll start by showing you the basic idea of a bomb calorimeter. Bomb calorimeter is where you have some for example, maybe a steel wall container. So its volume is incapable of changing. And you're doing some kind of a reaction in it. Let's say it has a thermometer sticking out of it as well. And we know that delta E is equal to Q plus W. But, now let's go back here. If W is the pressure times the change in volume, but if the change in volume, if the volume cannot change, if that volume is 0, then work is 0. So in the case of a bomb calorimeter, because this volume is fixed and cannot change, work is 0. And that means that in a bomb calorimeter, all of the change in energy is from heat flow, Q. And we'll call that Q, Q sub V. That means Q at constant volume. In comparison, a coffee cup calorimeter, let's envision a styrofoam cup, so to speak here. You might have a coffee cup calorimeter and there might be a reaction taking place, and you might even have a fancy lid, but it's not airtight. Since it's not airtight, anything that, any gas that's produced is actually able to leave. And you can also have a thermometer in your coffee cup calorimeter as well. So it's a little different here. So delta E is equal to Q plus W, but because volume could change, like literally if a gas is produced and it expands out, it's getting a larger volume. So there is a work component. So our work, we know that's equal to negative P delta V. So if I, just plug that in, so delta E is equal to Q minus P delta V. And if I rearrange that and solve it for Q, Q is equal to delta E plus P delta V. Now remember, that's the energy minus work. It looks like it's energy plus work, but remember that the work is a negative value, so this is really what it is. Well, by definition, delta E, when you get rid of the work component, is called delta H. That is known as a change, delta, in enthalpy. So Q in a coffee cup calorimeter is equal to delta H, and we call that Q, Q sub P. And Q typically has units in joules or kilojoules. The only difference you'll often see, although it's, they are equivalent, is usually Q is in joules or kilojoules, and you'll often find that delta H's units are referred to more in joules per something, joules per mole, or kilojoules per mole. So that kind of wraps us up looking at energy, looking at work, and looking at some calorimeters that are going to be used for measuring changes in energy. Next thing we're going to look at are what are some equations to know, but that will be the next.